So I'll be discussing two topics that have to do with the framework for doing statistical inference with representations of probability measures in reproducing kernel Hilbert spaces. So I will first just start by introducing the concepts of reproducing kernel Hilbert spaces and the associated metrics on probability measures that arise from there, and give you these two applications. So that's just the outline of the, that's just the outline of the talk. So first we will have these preliminaries of these representations that are called kernel embeddings. So what is this reproducing kernel Hilbert space? So one way to define it is just as a Hilbert space of functions on some generic domain. So I'm not really saying anything at this point about this domain. I'm just going to call it X. And I will require that this space of functions has an evaluation functional that is continuous at every point in the space. So, for example, that property is not satisfied by continuous functions that live in an L2 space, because you could have a situation there where you would have convergence of a sequence of functions in L2 space in norm, but not pointwise. So that cannot happen in a reproducing kernel Hilbert space. So it's a space with very nice structure where norm convergence actually implies pointwise convergence. So that's one way to define it. The other way is to do with this notion of a kernel function. So you can show that for every reproducing kernel Hilbert space, you can assign to it a unique positive definite kernel function, that's just a function that takes two arguments in your generic domain. And it satisfies these two properties, that when you fix one argument of this kernel function, that lives in this RKHS. And moreover, the representer of evaluation is exactly this kernel with one argument fixed. So that's exactly why this evaluation is actually continuous at every x, because this representer of evaluation, which we call k.x, actually lives in the space. So you can start the other way around. You can say, I'm going to start from a kernel function, then I'm going to construct this space of functions. And what does it look like? Well, it looks like these k.x guys, essentially, all linear combinations of them, and then completion with respect to pointwise convergence. And so if you have something like a Gaussian RBF kernel, then each of these k.x functions will be Gaussian bumps at point x. And you're just taking a linear combination of them. So you can see that you're actually modeling quite a flexible space of functions this way, by taking linear combinations of these, getting this blue function, which is essentially a linear combination of Gaussian bumps. Okay, so that's all quite nice, but it doesn't really relate too much to statistical inference and machine learning. So how does it actually get into this game of actually doing some statistical inference? So, well, I've said a lot about this k.x mapping. So this is this Gaussian bump at x, or a kernel, any positive definite kernel with one argument fixed at x. So you can essentially treat this as a feature map of your point x in your space. And now you know that this is something that lives in a particular Hilbert space, in a particular feature space. In a way, you can think of it as replacing a feature space representation of your data point x. That would be classical. So you would take a data point x, maybe it's a paragraph of text, and you're taking certain features, you're taking certain measurable quantities of that data object, and you're stacking them into a vector and then running something like logistic regression, perhaps. So kernel trick essentially says, well, I don't really care about this explicit representation in terms of the vector features. I'm just going to treat this k.x as my feature, and I'm going to take the inner product between the two features, and I will get the kernel itself. So I'm essentially doing some kind of implicit linear algorithm when I'm just working with these features k.x. And this is bread and butter of many machine learning algorithms. It has used widely to construct nonlinear algorithms for classification and regression and so on and so forth. And it also provides a nice framework to actually do machine learning on data that does not live in Euclidean spaces. It lives on some kind of non-Euclidean structured domains. For example, you can do machine learning on text or on graphs and so on and so forth. Okay, so what is this embedding? So it's taking this concept only one step further. So now that I have this feature map k.x, and I take a probability measure p, so now I'm going to say that my domain x is something I can define probability measures on. So now I'm just going to take the expectation of this canonical feature k.x, and that will be my embedding. So you can think of this as some kind of transform of your probability measure. That's exactly what it is, and it's in a way a generalization of a characteristic function, as we will see. So that also replaces a representation now of a probability measure, not of your individual data point, that would use explicit features and then take expectations of them. So you would replace expectation representation in terms of moments with this implicit representation that is your kernel embedding. So this expectation of the kernel embedding, that's some expectation over a Hilbert space, could be potentially infinitely dimensional. So that element mu kp of a Hilbert space has some expansion in some orthonormal basis, has some explicit coordinates, but I don't care about those coordinates. The only thing I care about is that if I take inner products between the two representations, that gives me back just the expectation of the kernel function itself, and I can easily estimate them. So now this gives a very flexible framework where one can do things with these embeddings of probability measures, where you can do non-parametric hypothesis testing for the two-sample problem, for independence, for conditional independence, and so on and so forth. And this has attracted a lot of attention in the last 10 years or so. Okay, so now that I have these embeddings, so what can I do with them? Well, the first simplest thing I can do, I can measure distances between probabilities. So this is called maximum mean discrepancy between two probability measures P and Q. So I just take embeddings of both and I measure distance in this Hilbert space. So this ends up having a very nice interpretation as being an integral probability metric. So it's also this expression on the right-hand side, which is trying to pull apart expectations with respect to one measure and with respect to the other measure as much as possible over a certain class of functions. And this class of functions exactly ends up being the reproducing kernel Hilbert space corresponding to K. Okay, so you have this example here where you have a blue density and a red density, and this green density is actually where this supremum is achieved. It's sort of a witness for the difference between these two probability densities, which is large in amplitude and positive, where blue is bigger than red, and large in amplitude and negative, where red is bigger than blue. Okay. So you see that the choice of this class of functions is crucial here, because if I take it to be too rich, if I take all continuous functions, then I will proclaim all probability measures different, and if I take it to be too simple a class of functions, then I will miss the important differences between probabilities. Okay, great. And for a very broad family of kernel functions, this notion of a distance between probability measures is a proper metric in the sense that this embedding is injective. So these include kernels that are widely used in machine learning. And moreover, under some weak assumptions, you can show that this also metrizes weak star topology convergence in distribution, in the sense that you get convergence in distribution if and only if you get convergence in MMD. So it's indeed, for certain choices of kernels, a useful notion of distance between probabilities. Okay, so I'm just listing here some applications of this framework of MMD. It's been quite popular recently in machine learning literature. So I mentioned these non-parametric hypothesis tests, but there have been some recent applications as well in terms of training generative neural nets for image data, where this is used as a criterion, this notion of distance between probabilities. So you have some data that's observed, you fit the model, you generate samples from the model, and you look at this distance between the samples that are generated from the model and so on. And some more interesting applications in this, including this automatic model check-in and criticism in automatic statistician by Zubin's group. So I will be discussing this last point here, where I use this MMD as a similarity measure between observed and simulated data in ABC, which you will see arises quite naturally in this context. Okay, I think in the interest of time, I will skip these two slides, which essentially say that you can do independence testing as well with this notion of embedding of probability measures. You just take an embedding of the joint distribution, embedding of the product of the marginals, you compute distances in Hilbert spaces, everything's nice and simple. It just boils down to estimating certain expectations. To do a proper non-parametric hypothesis test, you need to characterize null distribution of these estimators, and that's also quite straightforward using the theory of U statistics and V statistics. Okay. So it also has a nice interpretation, actually, this notion of a measure of dependence using these kernel embeddings. So if I say have here some sample from a joint distribution of images of dogs and some paragraphs of text that are describing them, and I want to test for dependence between these, then essentially what this V statistic that I would be computing boils down to is forming a kernel matrix on these images and kernel matrix on these paragraphs of text, and then looking at some kind of notion of an inner product between these kernel matrices. So if I think about the kernel matrix as a similarity pattern within the sample of images, and similarly for text, then what I'm doing, I'm measuring similarity between similarity patterns. And if that's larger than what can be attributed to chance, then indeed this is evidence against the null hypothesis. The two are independent. Okay. Okay, so that was all broad introduction into this notion of MMD. So let's see how it can be useful in the context of approximate Bayesian computation. So this is the topic of an AI stats paper that was published with some colleagues from the Gatsby unit at the UCL. So I will give you just some motivating example. Doesn't really matter what it is. So it comes from measuring population dynamics of this guy, of blowfly. And there is some relatively complicated discretized ODE that actually describes evolution in time. And what is important here is that there are some latent variables that I don't know how to integrate, and therefore my likelihood is intractable. So I have to use ABC to actually simulate data and try to measure some kind of discrepancy between the observed data and the simulated data. Okay? So my data set is a time series like this, so it's not immediately obvious how I would go ahead and measure this kind of distance between the two. So because in the context of ABC, I would have to choose this notion of a distance between the observed and the simulated data. Okay. So this is just an overview of ABC. So essentially, you choose some kind of notion of distance between the observed and the simulated data. You construct this kind of kernel, which is not necessarily the positive definite kernel from the beginning. So this is just a kernel in the ABC. And then essentially what you're targeting is the approximate posterior that is based on this notion of a distance between the observed and the simulated data. And while there is obviously an approximation due to this parameter epsilon here, there is another approximation that's much harder to quantify, actually, that arises from the fact that typically this kind of distance between the observed and simulated data that you would be using is not going to actually go through sufficient statistics of the data. So what you would typically do, right? So you would take your observed data, or the other way around, your observed data, your simulated data, and you compute certain features from it. You take certain summary statistics, you stack them all into big vector, and then you measure Euclidean distance between these vectors. So this kind of reminds us of something that perhaps we could do something a little bit smarter than that, rather than for every problem handcrafting individual features every time. Why? Well, because if these summary statistics are not sufficient, then you're introducing this additional bias. You're not even targeting the approximate posterior of the parameters given the data, you're targeting the approximate posterior of the parameters given those summary statistics. And if you have a very complicated model, this kind of bias is very difficult to quantify. Okay. So what would you do then? Well, you would add more summary statistics to ensure that that they are more sufficient. But then you would compute this kind of distance on a higher dimensional space because you're increasing into a bigger Euclidean space. And without appropriate calibration of these distances, you would just get the higher rejection rate. So there's this kind of trade-off between sufficiency and the rejection rate. And so what is our idea? Our idea is the simplest one possible. So you already get that I was talking about extracting specific features. So rather than extracting these specific features, we're just going to use this non-parametric distance, this MMD between the observed and the simulated data. So I do not have to handcraft the summary statistics. Obviously, for a specific problem, if I know how to handcraft very good summary statistics, I probably don't have to do something like that. But if I want to do this in a more automated way, then as we will see, it's a good choice. And so why, I just told you that like if you actually add more statistics, then you're in a higher dimensional space, so you're in trouble, so you get a higher rejection rate. And now I'm telling you actually use this MMD, which is essentially doing something in an infinite dimensional space. So it seems like a crazy idea. So why would that even work? Well, it turns out that this notion of MMD actually penalizes the higher order moment. So even though it's computing some kind of L2 distance on summary statistics, it's really weighing down the contribution of the higher order moment. So the rejection rate actually does not blow up. So this is due to thinking about these kernel functions in terms of their Mercer expansions. So the actual details are not too important here, but we can just say that if I take a positive definite kernel function, then I can write it for a continuous kernel on, say, compact domain. For simplicity, I can write it in this kind of form, where these ER functions are some functions that are increasing in complexity as I increase R. Okay. So the actual details will obviously depend on the choice of the kernel function, but for example, if you're using this Gaussian RBF kernel that everybody in machine learning is using, then these would be Hermite polynomials of increasing order. So for R equal to 1, they will have 1 bump. For R equal to 2, they'll have 2 bumps, and so on and so forth. So they're becoming more complicated as R grows, and these coefficients lambda are decaying geometrically. So now when I'm actually computing my embedding, it's essentially taking the expectation of these Hermite polynomials that are weighted by these eigenfunctions, and because the eigenfunctions are decaying geometrically, actually you will get that the contribution of these higher order moments that correspond to these complicated functions is fairly small. So even though you're actually computing this L2 distance on an infinite dimensional space, what we see in practice actually on this algorithm is that rejection rate does not blow up. So that's the algorithm. There's really nothing in there. We just say use MMD. And so just going back to this example. So I had this complicated model. And what I'm going to compare the method to is some previous literature that was handcrafting the summary statistics for this. So you see, you have this time series. So what kind of features I compute? Well, I'm going to look at some quantiles, look at some first order differences, some maximal peaks, these kind of things. So very specific, very much handcrafted for this problem. And yet, even though you're using these summary statistics that are handcrafted for this problem, whereas this thing is just saying use this MMD, just compute this empirical expectation of the kernel function, just look at the distance between them. Actually, in terms of this metric, which is essentially once you've once you generated samples from the posterior and obtained your posterior mean, and then you sample given that posterior mean, how far away are those handcrafted summary statistics from the observed ones, this method is actually performing better, which was a big surprise for us at the beginning because actually all of these other competing methods, well, I guess not all of them, but these three are actually using this specific choice of summary statistics. And I'm measuring performance in terms of those summary statistics. But this additional bias that's introduced due to insufficiency of them is actually so severe that you would see improvement with the method that's non-parametric. So now obviously very direct and fair criticism of the approach that I've presented is I'm using a kernel method that's computationally expensive. Right? I'm using this in the context of ABC, and I'm computing these MMDs. They are actually quadratic in the number of observations, so it doesn't make sense, right? Why would I do this when I can just generate more samples from a simpler model and I get better performance? So that's why we have investigated these alternative approaches that are essentially now approximating the original kernel method using explicit basis functions, and we do not really see any difference in performance. So that's again surprising, because these are explicit summary statistics that in the limit will behave like this non-parametric version, and they're still actually giving the same performance. Okay, so that's just the ABC application. I don't know how much time do I have? 10 more minutes. Okay, so that just I will wrap up this first part of the talk about ABC. So basically, the take home is if you don't really have much time to spend on handcrafting these summary statistics, and you don't really want to worry about the insufficiency of it, of them, then this MMD can be a useful approach just to run something that at least you've got rid of the insufficiency bias. You still might run into troubles due to ABC approximation, but we kind of like think about this as sort of a new way to think about the constructions of these summary statistics. And moreover, I didn't tell you anything about where that kernel came from, right? So I said you don't have to choose summary statistics, but you just use this kernel method, but then how do we choose the kernel? So that's what the next part of the talk is about. Because you will rightly be suspicious at this point of the method. Where did the kernel come from? So if you're actually doing support vector machines or something like that with kernel methods, then typically there will be some kind of framework for you to tune hyperparameters of your kernel function, some kind of guideline to how to actually select them. You could use cross-validation, you could use test error on the held out data set. If you use a GP model, so you're sort of doing a Bayesian version of kernel methods, then you have your marginal likelihood. You have some kind of handle on the choice of the hyperparameters. But in this kind of context, for example, inside ABC, there's really no gauge to what a good hyperparameter choice would be immediately. And also in the context of hypothesis testing, when I'm just doing a non-parametric hypothesis test, and I would want to also select the hyperparameter along at the same time as doing the test, then that brings all kinds of other considerations, because you would have to also worry about the multiple hypothesis testing issues and so on. So what I'd like to present here is a different way to think about these kernel embeddings that gives you a gauge on the choice of hyperparameters. So actually what people end up doing in practice, if you corner them and ask them, well, what kind of kernel did you use? I just use a Gaussian RBF. So how did you select the bandwidth? I just use median heuristic. So what does that mean? I just take interpoint distances between all the samples, and I just proclaim that to be my bandwidth. So that means if I form my kernel matrix, the entries are not all too large, and it's not like completely diagonally dominant. So it kind of makes sense, and there is some theory that says that this might be a good idea, but it just remains a heuristic. And as we will see, there are ways in which this median heuristic can break completely. So how do we how do we come to this different approach to modeling embeddings? Well, what are we doing? We're doing some kind of means on Hilbert spaces. They are infinitely dimensional. And because I'm just doing empirical means on very high dimensional, infinite dimensional spaces, then you immediately start thinking, wait a minute, what about things like Stein's phenomenon? maybe I should be worrying about something like that. 5 minutes, okay, excellent. And maybe I should consider some kind of shrinkage estimator. And indeed, this has been considered in the literature. And it was shown that actually it does help. Using the shrinkage estimator does help in terms of testing power, in terms of performance in kernel PCA, and so on and so forth. Okay, well, it's shrinkage, so why don't I then dream of some kind of Bayesian estimator for this thing? Because if I have shrinkage performing well, then Bayesian should surely also do well. And that's what we embarked on doing. But there are two challenges, obviously, because I have a thing that I'm estimating that actually lives in certain very specific RKHS, and I need to construct a valid prior on this RKHS. And then I also need to think about what the likelihood of the observations given the kernel embedding is. So I think I will skip some of the technical details here in terms of these priors. It ends up that due to certain well-known results, actually, that if you actually sample from a GP, which is a natural choice of a prior over an RKHS, but if you sample, if you sample from a GP with a kernel K, this will actually fall outside of the RKHS with kernel K with probability 1. So it may appear as a surprising result, but actually GP with kernel K is not an appropriate prior on the RKHS HK. But we can actually get around that by using convolution of a kernel with itself. So this is actually well known by some previous results. And so this has an interesting interpretation, for example, that if you want to sample from, if you want to generate a valid prior over an RKHS with just this Gaussian RBF function, just a stationary translation invariant kernel, you have to sample from a GP with a non-stationary kernel. That was a bit surprising for us. And then, like, once we've constructed this prior, we just think about what the likelihood would be. And in this case, we went with the simplest possible model, which just assumes that given the true embedding at point x, my empirical embedding that I actually observed, because that's based on the data, that's just the empirical mean I'm computing and then evaluating at x, is just a Gaussian that's independent everywhere. So this is clearly a terrible model for what's going on, because here I have P of an evaluation of one smooth function given another smooth function. So this is really not a good idea. But as a proof of concept, surprisingly, it actually recovers that shrinkage estimator that was already present in the literature, which was also surprising to us. So, okay, it's really a bad model, but actually that's what corresponds to the shrinkage estimator that's used in practice. So we recovered the shrinkage estimator, and now because it's a Bayesian estimator, we also get uncertainty estimates. But that's not actually, I will skip through a couple of these things, but that's actually not the most important aspect of it. Actually, it turns out because we're using this very simple likelihood and a GP prior, we can integrate out our embeddings and get the marginal likelihood of the data given the kernel parameter. Okay? Because I've put the model on mu theta, I've built a likelihood of mu hat theta given mu theta. Mu hat theta depends on these x's. There's some kind of Jacobian transformation going on, so details are not too important. But we get a form of the marginal likelihood of the actual observations given the hyperparameter. Okay? And that can now be utilized for choosing this hyperparameter. And there's some nice tricks here in terms of how to exploit this Kronecker structure, but that's just a computational trick. And so let's just look at what this likelihood looks like. So here I have a bandwidth of my Gaussian kernel, and here's the data set. So it's a bit weird. So what's going on? It's like a mixture of these 9 Gaussian blobs, and I'm doing a 2-sample test where I want to differentiate between 2 mixtures that have locations at exactly the same points, but the covariance structure of each of the blobs in one of the samples is just slightly different. Okay? So this is a really challenging problem, Even though just a two-dimensional simple problem, we can visualize it. But if we want to run this kind of automated test and just select the bandwidth according to this median heuristic, it will just over-smooth everything, because median interpoint distance between these samples is much larger than the interesting scale where the difference occurs. Okay? And indeed, if you actually plot this marginal likelihood that we've derived of the data given this bandwidth parameter, it has two modes, as you would expect from a mixture model, right? So it has a mode there, which is this global length scale that kind of corresponds to this median heuristic. And then it has this other mode that corresponds to this interesting scale where the differences occur. So if you now run testing with this, the length scale chosen using this marginal likelihood, you would obviously get an improved power of the test. Okay, so that's it. I would conclude there. So we argue that this marginal likelihood can potentially be a drop-in replacement for this median heuristic that's used in literature everywhere where there are no clear gauges on how to select hyperparameters. And thank you very much.